next intermediate is carbene. The divalent carbon containing two non-bonding electrons is called as carbenes. The divalent carbon containing two non-bonding electrons is called as carbenes. When the carbon containing molecule having two polar covalent bonds, these two polar covalent bonds undergo homolytic cleavage. When these two undergo homolytic cleavage, you are going to get the divalent carbon containing two non-bonding electrons and the free radicals. This divalent carbon containing two non-bonding electrons is called as carbene. This is 6 electron species. These are 1 2 3 4 5 6, hence it is 6 electron species, hence it is electron deficient species. It is electron deficient species. It is containing 6 electrons and it is electron deficient species. And due to the electron deficiency, it acts as a strong electrophile. Due to its electron deficiency, it acts as a strong electrophile. And this is one of the important intermediate in the organic reactions. And let's discuss about the structure of this carbene. The carbene exists in two structures, in the two forms. One is singlet state and another is triplet state. It can exist in two states, singlet state and the triplet state. In the singlet state, the carbon is sp2 carbon. This is the structure of singlet carbene. Here you can see that this is sp2 carbon. One sp2 orbital is bonded with s orbital of hydrogen. Another sp2 orbital is bonded with s orbital of hydrogen, and this is the sp2 orbit. sp2 orbital. This is sp2 orbital, and you can find the one vacant p orbital. One vacant p orbital is there on the carbon, and the two non-bonding electrons are there in the sp2 orbital. Two non-bonding electrons are in the sp2 orbital. These are paired. These two electrons are paired in the sp2 orbital. Hence, this is the structure of this is bent structure. The bond angle between this hydrogen 103 degree, and there is no free electrons. Hence, it is diamagnetic. The singlet state is diamagnetic because there is no free electrons. These electrons which are there in the sp2 are paired. Hence, there is no. This is diamagnetic in nature. Let's calculate the total spin of this singlet state. 2s plus 1. The two are paired, so that the spin of this one electron is plus 1 by 2 and the another electron is minus 1 by 2. Hence 2 into 0 plus 1 is 1. Hence the total spin is 1. Hence it is singlet state. And the triplet state, in the triplet state, carbon is sp hybridized. Sp orbital of this carbon is bonded with s orbital of hydrogen. Another sp orbital of this carbon bonded with s orbital of hydrogen. This is one p orbital. This is another p orbital. The two non-bonding electrons on the carbene are one in the one p orbital, another is in the another p orbital. But these two are not paired, because one is in the one p orbital, another is in the another p orbital. The bond angle between this hydrogen and hydrogen is more than 136. It is considered as the structure is considered as linear structure. The triplet carbene structure is considered, geometry is considered as linear structure. These two electrons are not paired, hence it shows the paramagnetic property. Let's calculate the total spin of this triplet state. 2s plus 1. These electrons are not paired, hence the spin of this one is plus 1 by 2 plus 1 by 2. Hence it is 2 into 1 plus 1 equal to 3. Hence this is called a triplet state. And let's look into the stability of the carbenes. This is methylene carbene. You know that in the methylene carbene this is singlet state, this is triplet state. These electrons are paired, these are unpaired electrons. These are in the p orbital, these are in the sp2 orbital. And out of the singlet state and triplet state, which is more stable? Here we can you see that this is in the sp2 orbital, these are in the p orbital. due to the repulsion in the singlet state, due to the repulsion of electrons in the sp2 in the singlet state, hence this is less stable. This is singlet state is less stable because of the repulsion than the in the triplet state. In the triplet state repulsion is less than the singlet, hence it is more stable. Triplet state is more stable than the singlet state when you consider the methylene carbene, but it is exactly opposite to the dichlorocarbene. When you consider the dichlorocarbene, this is dichlorocarbene. In the dichlorocarbene, this is singlet state, and this is triplet state. In the singlet state, both the electrons are in the sp2 orbital. In the triplet state, one electron in the 1p orbital, another electron in the another p orbital. Here the pair of electrons are there in the chlorine. There are pair of free electrons are there in the chlorine. Chlorine involved in the pi back bonding, means it gives the electrons. Pi back bonding takes place when the chlorine is there in the carbenes. In the dichlorocarbene, the chlorine gives the pi, involves in the pi back bonding to this vacant p orbital. But here there is no vacant p orbital. Here the pi back bonding is less here in the singlet state. Here in the singlet state it is more, in the triplet state it is less. In the singlet state, pi back bonding from this chlorine is more because there is a vacant p orbital. In the triplet state there is no vacant p orbital, each p orbital having one electron each. Hence the pi back bonding is in the triplet state is less, it is more in the singlet state. Hence this singlet state is more stable than this triplet state. This is less stable. Hence in the methylene carbene, the triplet state is more stable because of the repulsion. In the dichlorocarbene, singlet state is more stable because of the pi back bonding from the chlorine to the p orbitals. Here we have taken the carbenes containing different halogens: fluorine, chlorine, bromine and iodine. Means dichlorocarbene, difluorocarbene, dibromo and diodocarbenes. We know that the singlet state is more stable than the triplet state, so we have considered only singlet states. Out of these four, which is more stable? Where the extent of pi back bonding is more, than that carbene is more stable. Here the p orbital is 2p orbital. Here also the carbon 2p orbital, this is 2p orbital. Here also it is 2p, here also it is 2p. So pi back bonding between this fluorine and 2p orbital of this carbon. Here the fluorine, the 2p orbital of this fluorine involves in the pi back bonding with this 2p orbital of this carbon. When you consider the chlorine, 3p orbital of this chlorine involved in the pi back bonding with the 2p orbital of this carbon. Here it is 4p and it is 5p. Here 4p orbital involved in the pi back bonding with the 2p orbital of carbene. Here 5p of this iodine involved in the 2p of this carbene. Hence more, where we can find the more pi back bonding, here it can easily, here pi back bonding is more favorable. Pi back bonding is more here, hence this is more stable. It is lesser than this dibromocarbene, lesser than the diiodocarbene. Hence the pi back bonding is more favorable in the fluorine, hence it is more stable than the chlorine. Chlorine is more favorable than bromine than the iodine. This is the stability order of the carbenes. And also we should know the some of the named reactions which can have the carbenes as intermediates. Carbyl, I will write some of the reactions. Carbylamine, reaction, Wolff rearrangement, and Raymer-Tayman reaction. These are the some of the reactions which can have the carbons intermediates in the mechanism. Okay, thank you.